Welcome to our final chapter on capstone case studies and the practical machine learning workflow. Here we tie the whole book together and put it to work end to end. We have come a long way since the spam filter in chapter 1. The hard truth every practitioner learns is that in the real world, the algorithm is the easy part. So let us walk the complete arc and then apply it across a sequence of capstone case studies. In this chapter, you will learn to describe the full workflow from problem to decision, translate a vague real-world problem into a precise task, and choose models and metrics that fit the cost of errors while watching for leakage in your data. You should also be able to use baselines to judge whether a complex model adds value, communicate results to technical and non-technical audiences, apply a responsible AI review throughout, and design a capstone that connects predictions to actions. This figure shows the end-to-end machine learning pipeline. Notice that the loop from evaluation back to feature engineering or even data collection runs several times before a model is ready to deploy. A real project, whatever the domain, tends to move through the same stages. We define the problem and the decision it serves, understand who acts and at what cost of error, then collect and inspect the data, clean it, and engineer features. The work continues. Split the data properly, establish a baseline, then train and tune candidate models. The next figure lays out this complete arc as one pipeline, from defining the problem all the way to monitoring in production. Here is that full pipeline, from problem definition to production monitoring. The feedback loop returns a drifting or stale model to the data so it can be re-engineered and retrained as the world changes. Every doomed project shares a root cause, a fuzzy problem statement. Predict customer churn feels like a goal, but a good definition pins everything down, such as predicting which active customers are likely to cancel within the next 30 days. That single sentence fixes the target, cancellation, the horizon of 30 days, the population of currently active customers, the user, which is the retention team, and the action, prioritized outreach. With the problem framed, the task type usually falls out, and the task type then points you toward the right data, models, and metrics. This table maps real-world goals to machine learning tasks, so you can see how a business question translates into a concrete learning problem. Our churn example is a binary classification problem. Each customer is labeled either churned or retained over the next 30 days. Before cleaning anything, get to know your data. For every data set, ask what a single row represents, whether a customer month, or a transaction. Data understanding outranks model selection. Cleaning turns raw data into something a model can learn from, and it is usually the least glamorous and most time-consuming part of the job. Pre-processing then adapts that clean data to the model you intend to use. Feature engineering is where domain knowledge becomes predictive power, and it often moves the needle more than swapping algorithms. We might derive tenure from a sign-up date, build lag features for time series, encode categories sensibly, or turn text into useful features. We can also extract image features with a pre-trained network or compute graph features for relational data. For churn, a raw sign-up date is nearly useless, but months as a customer, recent logins, support tickets, and failed payments are exactly the signals we want. To know whether a model will generalize, we must evaluate it on data it never saw, and how we split the data matters as much as the fact that we split at all. Here is the key point. Data leakage, when information unavailable at prediction time sneaks into training, is the single most dangerous bug in applied machine learning. It produces gorgeous validation scores and crushing real-world failure, so scrutinize every feature for hidden future information. Before celebrating a fancy model, ask, better than what? Baselines keep us honest in two directions, guarding against both false pride and false despair. Only now, deep into the workflow, do we choose the algorithm. Even here, the rule is to start simple and add complexity only when it earns its keep, because the best model is rarely the most complex one. A metric is a definition of success, so choosing the wrong one quietly aims the whole project at the wrong target. For regression, we have standard choices like mean absolute error and R squared, but the deciding question is always the cost of errors. A model that no one understands or trusts will not be used, and an unused model improves no decisions. So be ready to explain which features drive the predictions using tools like feature importance and SHAP from Chapter 24. Chapter 24 made the case. Here is the operational version, a checklist to run throughout a project. Is the training data representative? Are the labels reliable? Or do they encode past bias? Have we checked every feature for leakage, and do sensitive groups face different error rates? The checklist continues. Are the model's errors acceptable given their real-world cost? Is it explainable enough for this decision's stakes? Is privacy protected throughout? And where does a human stay in the loop with real authority? Our first case study keeps subscribers at a streaming service. The service is losing customers, and winning one back costs far more than keeping one. The retention team can call only a few hundred each week, so they need a ranked list of who to contact first. This code works the churn example end-to-end. It loads a public telecom churn dataset, repairs a charges column that arrives as text with a few blanks, drops the bad rows, and sets up pipelines that scale numeric features and encode categorical ones for several models. The baseline that always predicts no churn looks deceptively accurate because most customers stay, yet it finds zero churners, which makes it completely useless to the retention team. Here we see 10 subscribers ranked by predicted churn probability, with the true outcome revealed. The 4 real churners landed at ranks 1, 2, 4, and 7 near the top where the team would focus. The retention team has the budget to call 3 people this week, so only the top 3 of the ranked list matter. Contrast this with the baseline that predicts nobody churns. It is right about the 6 who stay, for an accuracy of 0.6, yet it helps no one. This figure plots precision and recall at K for the ranked churn list. At the team's budget of 3 calls, precision is about 0.67 and recall 0.5. As K grows, recall rises toward 1 while precision drifts down toward the base rate. Most supervised projects share a skeleton, so let us look at a general template you can reuse across problems. This template captures that skeleton. It loads the data, separates features from the target, splits with stratification to preserve class balance, then bundles scaling and a logistic regression model together in a single pipeline. Never trust a single model in isolation, so let us see how to compare several against a baseline. This code defines 3 models, a majority class baseline, logistic regression, and a random forest, then fits each one and prints its F1 score. That side-by-side comparison tells you whether the extra complexity is actually paying off. If a complex model barely beats the baseline, that is a finding, not a failure. It tells you the signal is weak or the features need more work. Documentation is part of the deliverable, not an afterthought, so let us build a simple model report. This snippet assembles a small report as a dictionary, recording the problem, the target, the chosen model, the primary metric, and the known limitations, then prints each entry. It is a lightweight way to make your assumptions explicit. The same handful of mistakes sink projects again and again, reaching for a model before the problem is defined, trusting data nobody inspected, splitting time series randomly, letting future information leak in, or reporting one metric that hides the real performance. More common traps. Skipping the baseline, so you never learn if the model adds value, defaulting to complex models when a simple one would do, and confusing correlation with causation. Avoiding these is most of what separates a strong practitioner from a beginner. If you are picking your own capstone, choose a problem with a clear, real-world stake, available data, a well-defined target, a sensible metric, at least one baseline, and a genuine comparison of models. This closing chapter assembled the whole book into a single practice. We carried churn from a vague wish to a ranked call list, then toured credit risk, forecasting, recommendation, medical imaging, and a RAG assistant. The lesson is that machine learning is not fundamentally about algorithms. For further reading, there are excellent end-to-end project guides, a thorough introduction to statistical learning, a deeper treatment of its mathematical foundations, and a practical code-first guide to hands-on machine learning with scikit-learn and Keras. You can also explore responsible AI guidelines and practical checklists, the scikit-learn documentation on pipelines and model evaluation, and tutorials on building and deploying complete machine learning projects. That brings us to the end of this chapter and to the end of the book, where the complete workflow and our capstone case studies come together into a single practice of applied machine learning.